Welcome to Global Trends. Please subscribe and hit the bell icon for more breaking updates. Picture two Neptune-sized planets barreling toward each other in deep space. An unstoppable collision millions of years in the making. In a single, cataclysmic moment, they smash together, unleashing more energy than all the stars in our galaxy combined, if only for a brief, blinding flash. Rock and ice vaporize instantly, forming a superheated, glowing sphere, a new world forged from the wreckage. This isn't science fiction, it's science fact. Our most powerful telescopes have caught the aftermath of just such a cosmic event. It's a front-row seat to the universe's most dramatic process, planet-making by destruction. We often imagine planets forming gently, dust and gas clumping over eons. But sometimes creation is chaos. Giant impacts like this don't just end worlds, they create them. These collisions can reshape a planet's size, composition, and destiny. Events like this likely shaped our own solar system, including Earth, billions of years ago. Imagine two Neptunes colliding. The explosion of dust and debris would be so vast, it could block out the light of its star from hundreds of light years away. It's a reminder the universe is dynamic, violent, and creative. Planets are not static, they're forged, destroyed, and reborn. Witnessing this aftermath is like finding the embers of a cosmic bonfire. For the first time, we're seeing a planet become something new through a titanic merger. How did we spot this cosmic crash so far away its star is just a pinprick of light? It started with a mystery. In 2021, astronomers noticed a sun-like star, ASASN 21QJ, dimming for months. The culprit? A colossal cloud of dust and debris, evidence of a massive collision. Digging into old data from NASA's JWST telescope, scientists found the system had flared in infrared years earlier, a sudden heat flash. That was the smoking gun. The heat from the planetary impact itself. The dimming was the dust cloud drifting into view. The earlier infrared brightening was the energy of the collision. By connecting these clues, astronomers realized they were witnessing the aftermath of a giant planetary smash-up. It was a triumph of astronomical detective work, piecing together evidence from different telescopes and times, but the details of the new world remained hidden. What was this newborn planet made of? How hot was it? How was it changing? To answer that, scientists needed a more powerful eye, one that could see through the dust and analyze faint infrared light. Enter the James Webb Space Telescope. The real investigation was about to begin. With the scene set, the James Webb Space Telescope, JWST, took aim at ASASN 21QJ. Webb's sensitivity to infrared made it the perfect tool to spot the faint heat of the newborn planet, hidden in swirling debris. In early and late 2024, astronomers used Webb to directly detect the thermal glow of the new world. No more guessing, just direct observation. Using its near-infrared spectrograph, Webb measured the planet's temperature and began to reveal its nature. The data confirmed. This was a compact, planet-sized remnant still hot from the collision. Webb's instruments broke the light into a chemical fingerprint, letting scientists probe the planet's atmosphere and composition. This was a leap from what happened to what's happening now. Each telescope played a role. Ground-based surveys found the event, NEOWISE confirmed it, and Webb delivered the details. For the first time, we could watch a planet's birth and evolution in real time. Webb's first data brought surprises. The new planet was cooling much faster than models predicted. Instead of a lingering hot world, it was fading rapidly, like a cake gone cold minutes after leaving the oven. Why? Maybe the impact spread material out, letting heat escape faster. Or maybe new, unexpected chemistry was at work. Theories were upended. Scientists realized there was new physics to uncover. Webb returned 9 months later. The spectrum had changed, but not as expected. Some materials faded, others brightened, evidence of complex, ongoing processes. Perhaps different materials were condensing at different rates, or new reactions were lighting up the debris. The aftermath was dynamic and chaotic, not a simple cooling. Webb's sensitive eyes captured this evolution in stunning detail. We weren't seeing a static snapshot, we were watching a planet's turbulent infancy unfold. The data revealed planetary collisions are far more complex and unpredictable than we imagined. This new world isn't just fading, it's evolving before our eyes. This discovery is a milestone in understanding how planets form. For years, scientists debated, do planets grow slowly from dust, or through violent mergers? The ASASN 21QJ event is the first direct evidence that giant impacts really build worlds. It shows that planetary systems can be radically reshaped by late-stage collisions, not just by gentle accretion. Such impacts may explain odd orbits and massive planets in other systems, and even in our own. The collision offers a unique lab to study matter under extreme conditions, far beyond Earth's reach. It echoes our own history. Earth's moon likely formed from a similar giant impact. By studying this distant crash, we learn about the violent origins of our solar system and ourselves. This discovery has raised as many questions as it's answered. Why is the new planet cooling so fast? Why is its light changing in such strange ways? Our models are missing something fundamental. Scientists are racing to develop new theories. Maybe the impact was off-center, or the planet's chemistry was unusual, or the debris is affecting cooling in unexpected ways. More Webb observations are coming, with new data scheduled for June 2025. Tracking the planet's evolution will help solve the puzzle, revealing what materials are present and how they change. Each new observation is a step closer to understanding the physics of planetary birth. This is science in action. Observe, hypothesize, test, and revise. The mystery of ASAS N21QJ is pushing planetary science into new territory. This distant collision doesn't just teach us about exoplanets, it sheds light on our own solar system. The event involved two ice giants like Uranus and Neptune. Meanwhile, Webb is also studying icy worlds in our own solar system, the trans-Neptunian objects beyond Neptune. These bodies are the leftover building blocks of our planets, and Webb's data shows they're surprisingly diverse. Some formed closer to the Sun and were flung outward, painting a picture of a chaotic, dynamic early solar system. The giant impact at ASAS SN21QJ shows the extreme end of planetary evolution. Our Kuiper Belt objects show the quieter, lasting consequences. Together, these discoveries reveal that planet formation is messy, violent, and ongoing. With Webb, we're witnessing the universe's creativity, one collision, one icy relic, one discovery at a time.